Welcome everybody to our monthly meeting. We're going to feature AK6R, Bob Brehm. He's the chief engineer at Palomar Engineers, Inc., which makes antennas, balloons, RFI kits, and other ham radio accessories.
Good evening, everybody. Tonight we're going to be talking about end fed antennas for portable emergency and stealth installations. We developed quite a few of our antennas over the years, and this particular antenna that we're going to be talking about is an end fed, but I'm going to go through a variety of different antennas to get you to the concept of this particular end fed. But it's used by the Jamboree on the Air Boy Scouts all across the world. And they actually named the antenna, and we called it the bullet because the feed part looks like a big bullet. They wanted one that could be thrown over the branch of a tree and land on the ground and still function. And that's the function of what we call our bullet antenna. But we're going to be talking about that. But before I go into the specifics of antennas, some of you may have known about Palomar Engineers. It was founded by Jack Althouse, K6NY, in 1965, and quite a few of the products that were developed by him, noise bridges and antenna tuners and all that, were copied by MFJ in probably, I think, the late 70s. And he got out of that particular business. At one point in time, he had about 100 employees. And when he passed away in 2013, the whole company was in a 10-foot by 10-foot storage area. And so my wife and I purchased that company because we wanted the name and also some of the other things that came with it. And in fact, it included all the original engineering drawings in pencil that he had developed over the many years, and quite a bit of history, not much in products, but quite a bit of history of the company and old manuals and those types of things. And so we took that company and we've completely revised it. It's a woman-owned business because it helps us with all our military contracts. So we do a lot of military work too. Anyway, the product line consists of all types of different ferrite core products and applications of those for RFI, but also in balloons, Ununs, and feed line chokes. We produce almost 5,000 balloons and Ununs a year, and we've got quite a few techs that work for us on a part-time basis and a contracting basis just to make a lot of the things that we have. Our antenna systems that we currently have are the off-center feds, end feds, which we're going to be talking about tonight, loop antennas, which are absolutely great. If you want to be the king of the hill on 80 meters, get an 80-meter loop. And we also do terminated dipoles with resistors in them, primarily for the folks that are doing frequency hopping. You can go from 1.8 megahertz to 30 megahertz in less than a second, and your antenna doesn't have to be tuned, and it actually works just fine. If any of you remember Kurt Sturba, he wrote for CQ magazine for many, many years, and I've taken a lot of those articles, republished them, and I put them up as downloads for free. You can download them and read them, and they're quite interesting, and there's a lot of humor in there also. We distribute the products directly through Ham Radio Outlet, who's been a dealer for many, many years, direct and in eBay, and we've just signed up a new dealer in Switzerland and also a new one in Chile. So we'll be in South America shortly. So let's talk not about RFI. We're going to talk about antennas. We're going to talk about basically a short overview of all different types of antennas and show you how the end fed fits into that cadre, because it's important to understand that principle. We're going to talk about dipoles, off-center feds, ZEP antennas, which are just really end feds with a special feed on them, and also loops. Popular end fed antennas, there's basically two different types. We'll talk about each one. How to choose it that fits your needs. Secrets of non-resonant end feds, which is the kind that we use, and typical configurations that work all the time. These are great for homeowners associations, putting them in your attic, running them for all different types of portable operations and stuff. And we'll talk a little bit about what you need to go with that, including feed line chokes, counterpoises. And we also have a product that we've coined. It's called the Coax noise filter. It works very well for common mode noise, and it can cut up to 6 to 7 S units of noise out of your radio system. And then how to solve some typical problems that you have with end feds. But they're being that they're unbalanced antennas, they do have some issues at times. So let's put our thinking caps on. Basically, antenna feeds, there's three different types. One is a center fed, a typical dipole, for example. If you want to get fancy, you can off center feed it. That allows you to work on multiple bands, or you can end feed it. There's different types of end feeds that have different characteristics. So depending upon what you want, you can choose either of those. So one of the things we'll talk about real quickly is dipole concepts. The dipole length is typically half a wavelength. They can be at different heights above ground, and their impedance varies from about 50 ohms to about 90 ohms. And so if they're low wavelength wise, they're in the 75 ohm range. And if they're a little bit higher, they're in the 50 ohm range. So you can feed them with RG6, 75 ohm cable or 50 ohm cable, and they seem to work just fine. The off-center feds come in basically two different flavors. There's the classic 1/3, 2/3, and there's also the 80/20. And the impedance of those is 200 to 300 ohms. And so generally you need an impedance transformer to make those work. And there are advantages of using 80/20. You pick up a couple extra bands that you don't get when it's 66/34. But we'll touch briefly on that. The feed point impedance is a function of height above ground. Unlike end feds, that particular function is not there, so you can feed them just about anywhere you want. So let's look at a couple of dipoles here and just give you an idea. Obviously, there's a half-wave dipole, half wavelength on each side. You need to have a balun with it, or your dipole becomes a tripole. Your outside of your coax will radiate. And so always put a choke up there. And by the way, that choke only works on transmit, does not work on receive. If you want to offset it a little bit, there's an example right next to it where you have a 1/3, 2/3, and either a 4-to-1 or a 6-to-1. If it's really high in wavelengths, like 3/4 of a wavelength or 1 wavelength, then a 6-to-1 tends to be better. In real terms, that's about 100 feet. 70 to 100 feet, you should change the balun. And our baluns, when we make off-center feds, they not only have the 4-to-1 built into them, they have a choke built into the same box. So it saves you the extra cost of getting those. Companies like Dipole and those have dipoles that look like dipoles because they're the same length on each side, but in fact, they put a coil in there, and the coils make them electrically a little bit different. So in fact, they really are an off-center fed. And there's an example of a 62-foot off-center fed on the lower left-hand corner there. It can do that just by feeding it off-center a little bit. And there's an example of how the dimensions are. It's 29 feet on one side, 32 on the other. And so if you're pressed for length and you want to work one band, you can do it on 62 feet rather than the normal 68 feet. And even shorter if you want to use loading coils on the thing. You can also do 66 feet for a 75 meter, 20 meter, or a 75 meter, 40 meter in about 90 feet too, by using little loading coils like you see there. So there's lots of different options and different ways to do it. And a lot of it is just space determined. How much space do you have and where can you put it? Our off-center fed, this is an example of what it looks like. We use the 80/20 rule basically. And by doing that, we pick up all the work bands, and we pick up 15 meters and 12 meters. And we also get 6 meters on it. Whereas the typical 2/3, 1/3, you do not get 15 meters, and generally you don't get 17 meters either. You get 80, 40, 20, and 10, and sometimes 6, depending upon how high it is. By just changing the feed line position or the feed point position, you can play with what bands that you have and which ones you want to use. We think just by changing the feed point and getting a couple extra bands, that's well worth it. Okay, there's a couple other concepts. It's called vertical dipoles. And again, you can make a vertical dipole like on the left-hand side. This is a 2-meter one that works as an off-center fed. You can do a sloper, which is a vertical dipole. You can put coils, loading coils in it. You can even phase them like the ones that you see on the right-hand side there. That's 4-phased folded dipoles for 2 meters, used on repeaters quite a bit. First type of antenna we'll talk about is a center-fed ZEP. This is a really popular antenna. It looks like a G5RV, but it has all kinds of characteristics that are much better than a G5RV. Basically 46 feet on each side and exactly 40 feet of ladder line. And the reason that you choose that amount is that multiple bands have a 1-to-1 match, and you don't really even need an antenna tuner. I've used this antenna for years. and works very well on all the bands. And so if you don't have room for a beam or you can't put one up, this ZS6BKW is a great antenna. We don't sell this particular one. We sell all the parts for it, but it's, if you don't know about it, it's absolutely a great antenna. Puts the G5RV to shame, which is basically just a 20-meter antenna. Just a quick recap, our loop antennas. Loops can be vertical, they can be horizontal. 80-meter loop is about 270 feet of wire, and a 40-meter loop is 142. The advantage of the loops is that they're a lot friendlier in terms of actual size and configuration. And if you use a 4-to-1 balun on them, they'll actually work multiple bands, and they'll work the whole 80-meter band, whereas a dipole typically won't do that without using an antenna tuner. So it gives you a background in general antennas, but now we're going to do a little bit of work on end fed antennas. And there's three basic types. There's an end fed ZEP, which is also known as a J-pole. There's an end fed half wave, which is popular. And there's also a non-resonant end fed. And so what we like to do is get the most bang for the shortest amount of wire. That's been our goal, but you can do that several ways. One antenna that's really good is an end fed half wave, also known as a ZEP antenna. This is an example of one for one particular band. You have a half wavelength on 40 meters, for example, it'd be about 65 feet long. You have a quarter wavelength of ladder line, and it's shorted on one end. It's open on the other end. Only one end is connected. The other one goes to a little short feeder, maybe a foot, 2 feet long. And the impedance is very high because this is what they call a voltage fed antenna. It's a half wave, and you have to feed it at a voltage point. And so if it's got a very high impedance at the feed point, and if you take a quarter wavelength, one of the characteristics of a quarter wavelength of transmission line, no matter what type of line it is, whatever the impedance is, it will be very small at one end and very high at the other. If you short one end and make it 0 and you tap up to the 50 ohm point, you can find a place where the SWR is virtually a zip or 1-to-1. And of course, it's a coax fed, so you do need a choke on that one also. But a very nice antenna. A lot of guys run those on 80 meters that on the vintage sideband net, which is a net that I run on Tuesday nights on 80 meters. We've got quite a few guys running just half wave ZEPs only on 80. That's all they use them for. If you take out the short and you just feed that ladder line into an antenna tuner, then you can make it work on multiple bands. But typically it works better if it's not a quarter wavelength, because you don't want to have to deal with that low impedance on multiple bands. Okay, here's a couple examples of J-poles. You've all seen these, I'm sure. The Cushcraft R5, R7, R9s, they're really end-fed half waves, but they have lots of coils in them for HF. You've probably seen the VHF. That's a 2-meter J-pole that's got a half wave on the bottom section, and then it's got the quarter wave or multiples thereof on the top part of it. The one on the right-hand side is for UHF. That's a 450. And you can see how it works inside. If you open the box, it's tapped up from the bottom. The bottom is shorted. That's where the 0 ohm point is. Tapped up to 50 ohms, got a little choke on it. And that's a pretty good antenna, very broadband and easy and cheap to make. They work fairly well. Now, the other type that when we get down to HF purposes, there's two types of end feds, end fed half waves and end fed non-resonant. So I'm going to talk a little bit about the end fed half wave. Some of its characteristics are important. It is multi-band, but it's multi-band really only on the even harmonics. And there's a problem there. So if you think about it, if you want to operate 3800, 3895, for example, on 80 meters, if you cut the antenna to work on that particular band, then it's not going to work in 40 meters because they'll be out of the band. So typically these antennas work really well at the low end of the bands, because if you cut it for 3.5, 3.6 megahertz and you double that, you're still in the band on 40. And if you cut it low enough, you'll be on the band on 20 and also on 10. All right. But if you want to work the other part of the band, you're back to using an antenna tuner again. Or in some cases, they can fudge the bandwidth by using a coil on there, which is what you see in the diagram here. But then your bandwidth becomes real small in 80 meters, and you got to use a tuner all the time to go more than about 50 kilohertz. It is long. It's a long antenna, typically about 120 feet long. uses the coil to shorten it, but it still needs a tuner for multi-band. You really can't work the work bands without really stressing the matching unit. The matching unit, again, this is a half wavelength antenna, so it's got high impedance, which means it's got high voltage. So if you're running it, for example, in this example, you see an inverted L with a sloper on the right-hand side. But that matching unit, if it's close to the ground or it's placed where kids can put their hands in there or animals can get to it, there's high voltage there. There's 1 to 5,000 volts on that feed point. So you really either got to insulate it or make sure that it's out of reach of anybody when you're transmitting. So for that reason, and you also have to have a super heavy matching unit. The problem with making 49 to 1s and 64 to 1s is they're not very broadband. They have to be compensated enormously. And once you get up to the 20 to 15, 10 meter range, they're not really 49 to 1 or 64 to 1. They change their impedance transformation, which means you got to keep diddling with the tuner. It does need a feed line choke. Again, any coax antenna does need a feed line choke. And typically in this case, the choke is placed about 18 to 24 inches below where you feed it, because this essentially is it's an off-center fed antenna with a very short section there. The matching unit does get hot with power on the non-harmonic bands. It will actually heat up, and some of the high-powered ones you may have seen on the internet, they have sometimes as many as 4 or 5 toroids sandwiched together in order to get over 1,000 watts in these things. They do get real warm if you want to run them on anything but the harmonic bands. An alternative to this is the non-resonant end feds. They're typically shorter. All right, our most popular one is a 71-footer, but we've run them all the way up to 307 feet. And you'll see in a minute why longer makes a little bit of difference, but only for getting into the really low bands. Typically, it's about 71 feet, not 130, and you can still work 80 meters with it. They're easy to deploy. You can throw the matching unit on the bottom, that little white matching unit you can see in the center of the picture. That's what we call the bullet, because it looks like a big shell. It does have a counterpoise wire on it if you want to use it, but in fact, the coax itself acts as the other part of the antenna. So if you think about this, this is really an off-center fed antenna. It's using the coax as part of it. Electrically, it's stopped at what we call a feed line choke before it gets to the radio, so it doesn't transmit into the radio. And then the main part of the wire, which can be in many different types of configurations. It is a current fed end fed, so it's low voltage and higher current right next to the matching unit. So it's a lot safer from that standpoint. And particularly when you have lots of Boy Scouts and stuff putting these in all different types of configurations, from a safety standpoint, it's a lot better to have low voltage than it is to have high voltage end feds. Those are the pros. Some of the cons are the coax does radiate, and it will radiate all the way back to where the choke is, but that's okay because it's a much shorter antenna, and typically that's not really a problem. You can put counterpoises on it. You can actually put a choke right at the matching unit as long as you have counterpoises on it equal to where the choke should have been. So in this case here in the picture, you see that the coax is about 50 feet with a choke on it. So you have a 50-foot counterpoise and you have 2 15-foot counterpoises. This is the configuration that we use at all the hamfests. We typically run 71 feet of wire, put it up about 25 feet on a fiberglass pole, throw a couple of 15-foot counterpoises out because normally it's on asphalt and you can't really put it into any type of ground. And then we go out to a cyclone fence or wherever we can attach it to, and then run it right back to the radio. This is what we ran here at the Yuma Hamfest, and we've also run it down here at the San Diego Hamfest and at Pacificon too. So it's a real easy thing to set up. It can be completely deployed and taken down in less than 10 minutes. So I'm going to do a little recap here of the differences between the two, and then we'll go into some specifics of how to set these things up and what the characteristics are of different lengths and stuff. The end fed ZEP typically uses ladder line for matching the coax. I like ladder line antennas except when it rains. That's my only complaint about ladder line antennas. End fed half waves, they work great on the even harmonics. They require a special high impedance matching unit, and there's very high voltage at the feed points. The non-resonant is shorter. It uses a simple matching It uses a 9-to-1 transformer, which is pretty common. It's a low voltage feed point and works many more bands when a shorter length. So for my money, that's a better configuration. So what we're going to do now for the next couple of minutes is talk about how do you set up a non-resonant end fed. And so here's a picture of what we had before, and we'll go into some of the details of how that works. Some of the antenna secrets, at least I call them secrets, is how do you determine the wire length to use? And that's how long is the antenna, how long is the coax, and how long is the counterpoise? How do you match the antenna to coax cable? How do you choose a configuration that fits the location? I have seen these in all different types of configurations, flat out. In fact, we won field day 4A division with just a bullet antenna on CW in San Diego one year. We did really well just using that one antenna. It was a horizontal, completely horizontal, and it was up about 3,000 feet, and we never got off frequency the entire time. It works in all different types of configurations. How to choose a feed line choke, where to put it, and all this stuff about noise filters. So let's go talk about how long they should be. So here's a little guideline that we have on our website, is how to determine the wire length. The one that HRO sells is 71 feet because it can work multiple bands. And depending upon the configuration, a 71 footer will work 80, 60, 40, 30, 20, 17, all the way through 10 meters. If you want to work all those bands, your coax has got to be at least 65 feet long, and you would place the choke at that point. If you want to work the lower bands, 160 and 80, you really need to be at least 155 feet long. I'm going to show you why in a minute, because I'll give you some SWR graphs of different lengths and different configurations so you can figure out if it's going to work in your installation. The coax cable is typically 50 to 75% of the antenna length, and the counterpoise and the radials they're non-resonant. So you do not use quarter wavelength anything in this antenna. It's called a non-resonant antenna. Why? It's not resonant in the ham bands. It's resonant outside the ham bands. And there's a reason for that, because in the ham bands, the typical impedance where we're matching it is right around 400 to 500 ohms on all bands, not just a particular set like the end fed half waves. So it's much easier to match and much more friendly configuration wise. You can zigzag it, you can make it go up and down, you can run it through attics, you can almost circle it on itself, and it still seems to work pretty good. So let's talk about some of the configurations. And if you look in the inside of that picture here, you'll see 5 little diagrams. One is completely vertical, other is vertical with an inverted L, the other is an inverted U right below it. There's a sloper that goes up with the feed point at the bottom. There's a sloper that goes down with the feed point at the top. In general, we use inverted L's like you see in the large picture because you get a little vertical radiation and you get some horizontal on the sloper part of it that's coming down. If you didn't want to do an inverted L and you wanted to just do a sloper, then put the feed point high, because that's where the current is. And there's not much current at the end of the wire. So it would work a little bit better with that configuration. But the inverted L is probably the most easiest one to use. And that's the one that the Boy Scouts typically use. They just throw the little bullet over a branch of a tree, typically 15 to 20 feet tall, and then they just run it out to another tree or a fiberglass pole or something like that. What are some of the things that will make the SWR change on these types of antennas? The configuration of the shape obviously makes a difference. The length of the coax feed line, use the recommended values, and I'll show you those in a minute. Usually you put a feed line choke or a noise filter, and that goes towards the radio end. You actually want the coax to be part of the antenna. Soil conductivity, if you want to really get gung-ho, you can install it over or near water. The length and the number of counterpoises. You can have counterpoises different lengths depending upon your individual situation, and that's one way to tune the antenna. So let's look at some typical configurations, and these are actual real-life things that I've plotted. I've got 3 acres here, so we do a lot of different antenna tests and things. And so this particular bullet was was a 31-footer. That's all it was, 31-foot fiberglass pole. All right, and it had 2 counterpoises at the bottom. And we did have to use a tuner, but the red line is the SWR. And this graph goes from 80, the light gray lines, the vertical bars are the bands, so 80, 40, 30, 20, etc. And the red lines are at the top are the SWR. The green and orange ones are the impedance and the resistance and the reactance. You don't have to worry about those, but it's the red ones that are important. But you can see on 80 meters, the SWR is, it's about 2.4 through most of the band. 40 meters, it's a little high, but it's because the length is fairly critical. 20 meters, it's a little high, but on anything like 17 meters is good, 15 meters is good, 10 meters is good. So just for a quick, put it up and use it. You could probably fine tune 20 and 40 meters just by changing the length of the counterpoises. But in this case, you have a 31 feet of wire and you have 15 feet of counterpoise. So you're feeding it at 15 divided by 15 plus 31, 46 foot total antenna length. And so you could either play with it where the choke is on the antenna coax, or play with the length of the counterpoises until you get to the band SWRs that you want. This is a real quick and easy, put it up in the air, take it down thing. The next one is a 55 footer, and things start to really straighten out at 55 feet. So the 3-to-1 SWR line is right down there, kind of in the middle, a little bit above the middle. And you can see that on 80, it's pretty high with 55 feet, but on 40, it's below 3-to-1, and in just about all the bands above that, it's below 3-to-1. And in most cases, it's about 1.5 to 2 on every band above about 20 meters. Generally, it's less than 2-to-1 across the whole thing. So length makes a big difference here. And again, this was 20 feet vertical, 35 feet horizontal, inverted L, couple counterpoises, and it works great on 6 meters too, by the way. If we go a little bit longer, we go up to 71 feet, some real interesting thing happens. Just about all the bands from 40 meters up are under 2-to-1. And most of them are about 1.5 to 1, all the way up to 6 meters. 80 meters is still a little high. In this particular installation, it's about 3-to-1, but certainly you can use a tuner to bring 80 meters in if you want to. This one happened to be inverted L again, and it had 100 feet of coax. The choke was at the 43-foot mark, and we did use a tuner on 80 meters. But you can see that for the most part, these antennas are designed so that the internal antenna tuner in most transceivers is enough to make it work. You don't really need an external antenna tuner, unless, of course, you're using a linear or something like that. This is a homeowner special. We made some 77 footers. And here, of course, the SWR is low on just about all the bands, including 20 and 15 meters and 12 and 10. This was 8 feet up on a fiberglass pole out to a fence. That's all it was, 8 feet up. The homeowner put it up at night and he took it down during the day. He had 50 feet of coax on it and a couple of counterpoises, and he used this all the time. He also has used this underneath his house eaves. So even though it's low, only 8 feet tall, he was able to get on the air and make contacts, and the SWR was pretty well behaved. When you get up to about 92 feet, now things start to change. Now, if you look at the gray bars going up and down vertically, you'll see most of the bands are under 2-to-1, including 160, by the way. So 160, 80, even 60 meters, 40 meters, 20 meters. Most of those are all under the 2-to-1 SWR. So once you get to about that length, magic things start to happen. This one was 20-foot vertical, 72-foot horizontal, and 2 counterpoises. And we actually took a little wire and we drove a nail into the ground. We ran a counterpoise to that nail. And that's the kind of response that we got. So a real simple antenna system. And it got pretty darn good results. Once you get to about 110 feet, things really starting to flatten out. This one was 25 feet up, 85 feet horizontal, and things get to be real flat the longer you get. 148 feet, now you see 160 popping in here nicely. This is 80 meters, even 60 meters right here is in. So once you get up to about those length, everything is just virtually flattens out. The 155 feet, again, almost the same thing. This is the 2-to-1 mark right here. So everything is under 2-to-1, all the way out through 6 meters, virtually everything. So if you had a choice and you wanted to work 160, then this is a really good length to do that. Although I've had people use them up to about 307 feet, and they've reported really good results with them. Here's a little recap of some of the numbers that we were talking about. A table of antenna length, the antenna feed point to the choke length. In other words, where do you put the choke from the feed point? And you measure this from the matching unit or the bullet matching unit back to the radio. So in the first case, if you had 102 feet of wire, you would put a choke 44 feet on the coax back from the matching unit. So your total antenna length is 146 feet. So you can see it's kind of like an off-center fed antenna, but we're using a 400 to 500 ohm matching point rather than a 200 ohm matching point like most off-center feds. And the choke itself can be something really simple. If you're running low power, if you're running under 500 watts, you can use RG8X, and you can see the choke on the left-hand side and the bottom there. It's just a simple round ferrite toroid. It's a $10 choke. If you want to get a little fancier, you can use the little box in the middle, which is a mini choker, and they're good for 500 watts, and they're about 4 or 5 times better than the single ring, and they'll certainly do the job. And for high power, you use the big tube on the right-hand side, and they're good for 3 kW. And by the way, our ratings really mean what they say. You can run 1500 watts FTA through that choke all day long, and it won't even phase it. It's really a good, our ratings are pretty conservative. As far as matching is concerned, these non-resonant antennas match best with a 9-to-1 transformer. This is what the little small bullet looks like, a little artillery shell. And it's got a counterpoise on the side, and the antenna feed point and the halyard hoist are all in the same piece of metal there. And you would feed it right between the two pieces of washer. The coax input goes on the bottom. In this format, we make them in 500 watts, and then we make a little bit of taller one, which is 1500 watts. And then we also make them in cubes if you want to attach the cube, for example, to a cube box to the side of a wall or something like that. We make those up to 5 kW. So the contesters that are running RTTY at 1500 watts will get the 5 kW ones, for example. This is the example of the high-powered ones in boxes. The one on the right-hand side is an interesting one. It's a 4-to-1 and a 9-to-1 built into the same box. So you can pick off the 9-to-1 on the top, just like you would with our bullet one. And if you want, in some cases, you actually get a better match with 4-to-1 on particular bands. Or if you want to play around with different lengths and stuff. So we put a 9-to-1 and a 4-to-1 in the same box. And in fact, we have a 9-to-1, a 4-to-1, and a 2-to-1 in the same box. These are unbalanced. These are called Ununs. They do require another part of the antenna, either the coax or a counterpoise. Feedline chokes come in several different types. There's feedline chokes, and there's also coax noise filters. This is a coax noise filter. It looks similar to a feedline choke, but I just want to give you kind of a heads up, FYI information on chokes in general. I mentioned before that if you put a choke at the antenna feed point, what it does is it prevents the coax. Most people know that coax has got 3 conductors, right? And so the outside of the coax braid, even though it's one piece of metal, it's 2 electrical conductors. And so the outside will actually radiate if you don't put a choke at the antenna feed point. And so that's the sole purpose of putting a choke at on any coax-fed antenna, is to stop that from radiation. You want to stop the coax. In our case, for our end feds, we do want it to work. We do want it to radiate, but we have to put a choke farther down the coax so that it stops where we want it to. But in general, if you do not put one there, what happens is that the coax will radiate, and the radiation may get into different things in your house and cause other issues. So if you do put a choke up there, whether you do put a choke or not at the antenna feed point, depends upon the type of antenna. But you should always have a really high impedance choke at the transceiver. And so what's the reason for that? If you think about it, your signal is going to be coming from the antenna down the center of the coax, but also any noise sources out there will also attach themselves to the outside of the coax. And so essentially, when you plug in your coax into your radio, you have 2 receive antennas. The outside of the coax is one receive antenna, and the inside of the coax is the other receive antenna. So if you put a coax noise filter at the end before it goes into the transceiver or before it goes into the amplifier, for example, it will then stop that outside noise from coming in. It makes a huge difference, particularly with vertical antennas, but it works on all coax antennas. There's different types. You've probably all seen these. They're snap-on chokes. To put it in perspective, each one of the little beads on a snap-on is with one turn through it is typically about 100 to 150 ohms, depending upon the frequency. Ferrites, as most of you probably know, are really frequency-dependent resistors. So they change resistance depending upon frequency. At the low frequencies, they have small impedance, typically 50 to 100 ohms per each bead. But as you go up in frequency around 2 meters, for example, each one of those beads is about 250 to 300 ohms. So they're actually, you need fewer at higher frequencies than you do at lower frequencies. The typical rule of thumb is you need at least 500 to 1,000 ohms in order for them to work and have any type of measurable difference. So the one on the left-hand side, for example, has got 5 beads on it. They're about 500 to 1,000 ohms, depending upon frequency. If you take a simple little ring and you put 9 or 10 turns through it, you'll get 1,000 to 4,000 ohms of choking. Real simple, easy way to do it. In fact, I came out with a product like that, and I can't believe how many people don't want to wind their own. They want to buy those, and I've sold just tons and tons of those things as a product. And HRO sells those too. And all it is a ring with a 3-foot piece of coax on it. If you want to get even better, you use a coax noise filter. It's just a really high impedance ferrite, multiple mixes inside the little box. Works really well. If you don't know too much about ferrites, here's a real quick review of it. You'll see here, if I have a coax, this happens to be a coax ring similar to the one that we have down here, but it's in a box. And this is a measure of its impedance. And you can see the impedance is going down as we go up in frequency. And that's just a characteristic of the ferrite itself. If you get smart and you put multiple types of compositions in a box, you can actually make it go up. And then it kind of tries to go down like the other one. But if you put multiple types of ferrites in there, you can actually make it carry out all the way past out here to 6 meters and be, 4,000 or 5,000 ohms almost the whole way. Whereas this one above about 30 megahertz, it just starts to peter down and it's down here around 1,000. So it's all a matter of how you put those things together. Like I said before, you need about 500 to 1,000 ohms, but to put that in a different perspective, because most of us think about S units and noise, I have a little table here that converts choke impedance into attenuation. So if you do have 1,000 ohms in a choke, it's basically about 20 dB of common mode attenuation. If it's 5,000, it's about 34. So as you go and have chokes with higher and higher impedance, it takes out more of that either transmit current or, saying in a different way, it takes out common mode noise that's being picked up by the outside of the coax. And I have people swear by our little noise filters. I can't keep them in stock. They're just a really good product for taking out the common mode noise. We put these antennas together. This is the one that HRO sells. They sell the antenna, and you can obviously buy all the parts, but you can buy the antenna with the matching unit, 71 feet. This is the counterpoise kit and the choke. Now, that's all one particular one. It's about $120 at HRO or direct. The prices are exactly the same whether you buy it direct or HRO. It doesn't make any difference. Or if you want, you can buy the individual parts separately. You can buy the antenna and the wire. You can buy just the matching unit. You can buy each one of these separately and put them together yourself. That's a real easy thing to do. Solving some of the end fed RFI problems, and these are problems that you'll have with any type of end fed, whether it's an end fed half wave or it's a non-resonant one like we have. And when you do have those types of problems, you may even get really good at it, and you'll get what they call the Worked All Neighbors Award. And this is an award that you can download for free, by the way, on the website. And there's endorsements for 5, 10, 15, 20, neighbors. If you're persistently interfering with your neighbors, you'll get an award. And if you want, and a lot of clubs have downloaded these and actually awarded them. It's funny. That's typically what happens if your coax is radiating or it's close to the neighbor. You'll work the neighbors and you'll get a knock on the door, and or your wife will come up and say, "Honey, I can't watch Dancing with the Stars anymore because you're interfering with me. Turn off your radio." But there are ways to let her watch her TV show and still be on the air. And we're going to spend a couple seconds on that. Typical RFI solutions, just in general, this is true for all antennas, is keep the antenna and the coax away from house wiring, including AC power lines, cable satellite feeds. They're all coax cable. And remember, the outside of the coax of the cable and satellite act as an receiving antenna. It picks up your ham radio signal like anything else, and it distorts cable boxes and those types of things. Telephone lines in your house, AC power lines, they act as great receive antennas, and they overload anything that's attached to them. Or these antennas can transmit spurious signals and noise into your antenna system, so it's reciprocal. If you own an LG washer dryer or an LG refrigerator, I can almost guarantee you it's a noise generator, and it's feeding noise into your AC power line, and your antenna in turn picks that up. And typically it's a couple less units. So there's real simple fixes to that. But a lot of the appliances that we have, at least in California, all motors have to be variable speed now in California, all new ones. And they don't vary the voltage anymore. They vary the pulses to the motor. So they're pulse width modulated variable motors, which means for hams, they're really noisy. That's a solvable problem. We have all different types of RFI kits for specific solutions like home theater systems and touch lamps and garage door openers and all that kind of stuff. If you ever put in LED lights in your garage, don't be surprised. Your garage door key fobs don't work anymore from the house or your cars. If you're experiencing issues with transmit RFI, remember all the wires that go into your radio or your amplifier, all of them can act as antennas, and all the RF from an amplifier does not go out the output connector. Some of it will actually leak through the other wires that are on there, including the AC power line. So we came up with these many years ago, the RFI kits for amplifiers and for transceivers. And in fact, the ICOM 7300 kit is one of our all-time best-selling kits. You want to put a ferrite on the coax, you want to put it on the DC power lines and also on any other wires that are coming in and out of your radio to stop transmit RFI going out, but also to stop noise coming in, because noise tends to be the limiting factor in our radio shacks these days. Your neighbors can also have problems, alarm systems, home theater systems, computers, telephone, DSL lines. A lot of times your computer will slow down when you're working on the radio, and it's because it's error correcting all the time. It's picking up your signals, and it causes errors in the digital pulses, and so it has to correct and correct and correct. Simple chokes like this will stop that problem altogether. Okay, we're going to have a 3 or 4 question quiz here. If you've been paying attention, I'll tell you what the answers are, and then we'll take a little bit of time for Q&A on anything you want to talk about. What are some of the characteristics of a non-resonant end fed antenna that make it superior to a half-wave end fed antenna? Obviously, you can tell I'm biased by the nature of the question. But so here's some of the answers. Non-resonant antennas will work on even and odd harmonic frequencies. Yeah, that's true. Remember, half waves only work on the even ones. Half waves have complicated matching units with high voltage. Non-resonant have simple matching units and lower feed point voltages. Non-resonants can work the work bands. Most of the time, the other ones can't, the end-fed half waves. Non-resonant antennas radiate as well as resonant antennas. A lot of people ask me, well, if it's not resonant, how does it actually work? It doesn't make any difference. If you match a wire to the frequency that you're transmitting on, it'll transmit just as well as a resonant one, as long as the length is large enough. And you saw by some of the SWR graphs in there that even a 71-footer will work on 80 meters, whereas you normally would have to have 130 feet. So the proper answer is all of the above is true, none of the above, and I have no idea. I was asleep during the talk. Question number 2 is, where do you place the feed line choke on a non-resonant end-fed antenna? Well, one choice is right below the matching unit to choke off all the coax shield radiation. But remember, you want the coax to radiate, right, in a non-resonant one, because that's part of the antenna. So that answer is not right. You can put it at the radio end of the coax, about 30% of the coax plus antenna wire length. Okay, well, that's an answer. Answer number C is in the middle of the coax length to balance the radiation. Well, that's pretty simplified thinking, and so that's not true. If you put it between the antenna tuner and the transceiver, nope, you're not going to put it there. End-fed antennas don't need feed line chokes. So of all those answers, the best one is really B as in boy. All right, a couple more questions. What is one of the best kept secrets in ham radio? Ladder line has more loss than coax. Well, that's not true. An antenna has to be resonant in the ham bands to radiate in the ham bands. Well, I just told you that's not true, so it isn't. All ferrites work at all frequencies, so you buy the cheapest. That is not true. If you've ever taken my RFI course on ferrites, you'll know that they all look the same, but they're all different frequency ranges. Quite a few times you'll go on eBay or Amazon and they'll say, buy 20 ferrites for $10 or $20, but they have no specs on them. You don't know what frequency range they're good for. You don't know how many ohms they are at any particular frequency. And you don't know even if they'll work for you. My advice is just don't buy them unless you know what the specs are. It's a waste of money. It's like buying a resistor without a color code on it. It may work, it may not, who knows. Answer D is coax noise filters reduce common mode noise level in your receiver so you can hear more stations. That's absolutely a true statement. And a lot of people don't know that if you put a really good choke next to your radio, you will get rid of quite a bit of the noise. And if you're using a coax antenna switch and you're switching multiple antennas into it, if you have an antenna switch with 3 antennas on it, remember, you're only switching the center conductors. So all the coax braids are hooked together. So anytime, if you're selecting antenna number 1, for example, you actually have antenna number 1 center conductor, you have antenna number 1 braid, you have antenna 2 braid, and you have antenna 3 braid. You have 4 antennas at any one time or using a mechanical switch like that. So the proper way to do that is you put a noise filter on every antenna before it gets to the switch, and then you've isolated each one from each other. And I ran into this problem when I was running a contest. I have a big log periodic antenna, and I have a whole bunch of loops all over the place. One of my loops is close to the power lines, and so I'm running on 20 meters, and I got so much noise. I said, where is this noise coming from? It turned out it was coming from coax braid of the loop antenna that I wasn't even using. And so I learned real quickly that if you put a filter in each one of them before the antenna switch, it makes a heck of a lot difference. Okay, last question. You should all get this one right. Which company is your best source for end fed antennas and RFI solutions? Here's our contact information. My name is Bob Brehm. I'm AK6R Chief Engineer. And you can usually get me just about all the time up to about 6 or 7 o'clock at night and after about 10 in the morning.